I'm going to tell you how we can estimate distances in the in astrophysics. I was going to say solar system. In astrophysics, so just because I'm saying estimate, I'm just letting you know that all these distances, they have a certain uncertainty, okay? So this is an estimation. We know it's not the exact number, so it's not the exact distance, but that's the best we can do, which is very good with the technology we have, or within the conditions we have, okay? So there are mainly three different ways of how we can estimate distances. So if I'm talking about things within the solar system where I can use astronomical units, check the previous video, to say these distances, I can use the method of radar. I'm going to tell you about this one. If I have nearby stars, I can use parallax. So how much the star seems to move in relation to the background stars, okay, within 6 months. I'll talk more about parallax in another video. And then if I have larger distances, so when the parallax angle is so small because the star is so far away, I can use another methods or other methods which use the apparent brightness. So how bright something appears to be from the distance that we are, so on Earth, knowing that the brightness decreases with distance because, you know, the star is spreading out, so the light is spreading out, so the bigger the distance, the more spread out the rays are, okay? With apparent brightness, I can use Cepheid variables, star luminosities, and type 1a supernovas. I can actually use more stuff, but I'll tell you all about it when I get to those videos, okay? Focusing on the radar. So using radar, oh, there is a vacuum cleaner right now working, so I hope this is not picked up in a video. So, using radar to measure distances and velocities. So, one way that I can measure the distances within the solar system is by using radar. So, all that I do is I send a pulse of radio waves of in the electromagnetic spectrum, and I send it from a radio telescope towards whichever the object I want to check, planet or an asteroid. The pulse hits the surface of that object and then is reflected back to the Earth. And then the telescope picks up the reflected radio waves and records the time taken for them to return. So my time starts when I send them, they get to the object, they get reflected, they come back, okay? So, and I did this in lesson and most of you could do it as well, the formula to figure out what is the distance of the object. So, first of all, I'm assuming, and this is a pretty good assumption, that all the radio waves are traveling at the same speed going to the object and back, which is the speed of light. So I'll say that I know that speed equals distance over time, so distance is time times the speed, but I have to divide the time by 2 because I need, the time that I get in my telescope is the time for the pulse to go and come back. So I divide the time by 2 because I want to know what would be the time to reach the object. This is what is going to tell me the distance. So using radar, this is the formula for the distance. C, the speed of the electromagnetic waves or the radio waves, times T, the time that it took for my pulse to go and come back, and divided by 2, all right? Now, I can use radar in other ways as well, okay? So there are other applications. So I can, for example, figure out the average speed of an object in relation to the Earth. All that I need to do is send 2 pulses separately by a certain time period or time interval, and I get 2 separate measurements of the distance. Now, we already know that distance equals the speed times the time, right? So I get 2 different distances. So the difference in between the 2 distances is going to tell me how far the object has moved in that time, okay? So I will get to know how much it moved away or towards us in that time. I can also get the object speed by doing the speed of recession, or actually approximation, equals the distance divided by time. So radar is actually quite useful and pretty accurate. The closer we are in astrophysics, the more certain we are about the distances. when we are thinking about larger distances, that's when we do more approximations, and that's when we are not as sure about the actual distance of the objects. But as I told you, it's still a pretty good guess. And then assumptions. Oh my god, I'm always moving this thing all over the place. So assumptions, we need to know, so when we are making these measurements, we also need to consider what we're doing that can make that our result is not 100% perfect or accurate, okay? So we need to know about the assumptions we're using. So our assumptions are that the speed for the radio waves is the same on the way and back. This is a pretty good assumption. This is basically true. So yeah, this is true at all times, so no need to worry. And that the time taken for the radio waves to reach the object is the same as the time to return. Again, this is basically something that is not going to be a big assumption. It's actually something that is happening, all right? So for this to be true, so for these two assumptions to be the speed of light must be constant, and the object speed must be much smaller than the speed of light. So I do not have any relativistic effects, which again within the solar system is fine, because for me to start to get relativistic effects, I would have to be at a velocity of 0.42 times the speed of light or more. So that's not really happening in the solar system. So all these assumptions are pretty good assumptions. The results that I get using radar are very, very good, okay? If I want to take more accurate measurements, I can use the Doppler shift, okay? So I can look at how the spectral lines in the objects change, okay, the frequency that I pick up from the object. And by looking at the change from the initial position, then I can figure out the velocity of the object, and then I can figure out the distance. I can figure out loads of things, but this is all for a different video, okay? So when we talk about Doppler, there's going to be a video which is going to have somewhere Doppler in the title. Then I'll tell you more about it, okay? At the moment, that's all that you need to know. I'm just going to let you here with some exercises in case you want to pause the video and do them. Otherwise, you can just leave. So I have here all these 4 different questions plus another question. So 5 questions. So again, pause the video if you want to do the exercises, and then the answers are these ones. Again, because I'm going to stop the video pretty soon, pause the video, check if the answers are right. If they are not, check on my resolution and at me making the me giving you the answers if it all makes sense. If not, drop me a message, talk to me directly, all of that stuff, okay? So I'll see you in another video where I'm going to talk about parallax, I believe. So see you next time and take care. Bye.